In this lesson, we continue on with our radicals. In this lesson, though, we're going to be doing operations with radicals, like adding, subtracting, multiplying, and dividing. One way to think about adding, at least, is it's just like combining like terms. Just like when you started learning how to combine like terms, you knew that the 2x and the 4x would go together, and they would give you 6x, but the 3y, it had to stay separate. All right, well, same thing with radicals. If you have like radicals, you would add them the same way. Remember, when we added 2x plus 4x, we only added the 2 plus the 4, and we kept the x. Same thing with adding with radicals. This would be a total of 9 radical x. This next example, number 3, we would want to add like terms. Well, these are not like terms. And so since they're not like terms, they cannot be combined. All right, then we started getting into a little bit more complex problems, like number 4. And so sometimes, as we get a little bit more complex, it looks like they are not like terms, but we can simplify them. And once we simplify them, then they would be like terms. I'm going to skip number 4. I'm going to look at number 5 and number 6, though. So number 5, first of all, thinking about that concept of like terms, these also are not like terms. And once again, they cannot be simplified. And the reason these are not like terms is they are different roots. So on number 3, we had some that were not like terms because there was a different, like a square root 2, a square root 3, those are different. But here it's because this is a square root and this is a cube root, and so we cannot put those together because they are different roots. But let's get back to what I was talking about a minute ago, that if we simplify it, maybe we can have some like terms. Now that's not going to work on number 5, but number 6 it will. So if we think about number 6 and we think about how to simplify number 6, well, 81, I want to think of the perfect cube that goes into 81. 27 goes into 81 and it goes in 3 times. And x to the 4th, I could simplify that to x to the 3rd times x. So now I'm doing cube roots. 27 is a perfect cube, so that's a 3. And the x to the 3rd is a perfect cube, so I'm going to bring that out as well. And then I have my cube root of leftover 3 and leftover x. Now this one is already simplified as far as it can go. So now I have like terms, and I just need to simplify those by adding those together. So I get a negative 2x times the cube root of 3x. And again, the main point on that problem was to simplify it so that you have like terms, and then once you have like terms, then you have your final solution. You can actually combine those now. Let's see if we can do that same thing with number 7. So for instance, this is a square root, this is a square root, this is a square root. We can consider this, especially because as I think about 28, I know that's 4 times 7. And 63 is 9 times 7. And this is a 7x, so I'm kind of on a good roll here. It's possible that these might start going together because they all have a 7 involved in them. So my first term, I'm going to simplify that to be 2 times the square root of 7x. Because the 4 comes outside, becomes a 2, the 7 stays there with the x. And then here I have a 9 and a 7, so the 3 comes out. Also, x squared, the square root of x squared is just x, so that needs to come out as well, and that's now just a regular square root 7. And then finally, this one can't be simplified any further, so I just have 2 times the square root of 7x. All right, now when we look at what we have a 2 square root 7x and a minus 2 square root 7x, so that minus itself is 0. That drops off basically. And what I'm left with is just 3x square root of 7. Because that 7 was not like terms with the 7x. But it did remain. There was nothing canceling out. These two canceled each other out. Again, I don't have time to go through every single problem, so we're going to skip number 8 for now. Let's look at number 9. We're going to do the same thing. That is, we're going to try to simplify these to create like terms. Well, 225, isn't 225 a perfect square? And I believe the square root of 225 is 15. And 144 is also a perfect square. And so we should get 45 square root x plus 60 square root x. And if I add those together, I get 105 square root x. So that is the concept of creating like terms so that you can combine them. Let's go on to the next one, which is multiplying and distributing with radicals. So a minute ago, we were adding and subtracting. We know some basics about multiplying, but maybe we don't know everything we need to know. So we're going to go into depth with multiplying. You see you have a binomial times a binomial. Hopefully you know that to do that, you're going to have to double distribute this and multiply it out. So I'm going to go ahead and do that. I'm going to multiply my 1 times these two terms and multiply my -5 times these two terms. Okay, so when I do that, I get 2 plus 1 radical 5 minus 2 radical 5, and then you might not know what this is. So let's talk about a negative radical 5 times a positive radical 5. Well, it's going to be a negative answer because a negative times a positive is negative, and we're going to multiply those numbers and get a radical 25. Well, what's the square root of 25? It's 5. So when I multiply those two together, what I get is a -5. Now what I showed you out here in the margin was kind of the long way. Hopefully pretty soon you're going to get to a place where you just know that if you have the square root of x times the square root of x, the answer is just x. And so that's what happened here. It was negative because there was a minus here. Okay, so we're not done with number 1 yet. Let's go back and keep going with number 1. We have some like terms. 1 radical 5 minus 2 radical 5. And we also have a 2 minus a 5. So 2 minus 5, that's a -3. And 1 minus 2 is -1 radical 5. Let's try it with number 2. Same process. We're going to multiply. And then again, we'll have to talk about, well, what happens when you multiply 3 radical 7 times 3 radical 7. And we'll get to that. But I'm going to go ahead and double distribute these. All right, so when I do that, I get 4 minus 3 radical 7 minus 12 radical 7. And then a negative times a negative is a positive. And when I multiply these two numbers together, I get 9, because 3 times 3 is 9, and square root 49, or in other words, 7. Because that rule we're trying to work on is anything times itself, if it's a square root times itself, it's just that whole number. So square root 7 times square root 7 is 7. Okay, so in other words, I have 4, and then this is 63, right? So 4 plus 63 is 67. And 3 radical 7 minus 12 radical 7 is minus 15 radical 7. So that's how you multiply two binomials that include radicals. Let's turn the page. Number 3 is very similar. The difference here is just they're both radicals. Remember, when you have a second power, you don't just distribute that. That is not how they work. What you have to do, you have to set it up to be a distribution problem. You have to multiply it all the way out. So we have to rewrite this in this form, and now again we're going to do our double distribution and we're going to work this out. I think that you have seen enough examples. Why don't you give this one a try? Pause it here and see what you get. Okay, so when you multiply it out, you get radical 2 times radical 2 is 2, and then when you have a radical 2 times radical 7, that's a radical 14, and you have another radical 14, and then you have your 7. The like terms are 2 and 7 add together to be 9, and radical 14 plus radical 14 is 2 radical 14. Now I have a short question for you. Would this equal 11 radical 14? No, it does not. Why not? They're not like terms. You can't add that to. It would be like if you said 9 plus 2x is equal to 11x. No, it's not. We know that. So neither is it 11 radical 14. Just remember that that does not work out that way. Number 4, because a minute ago I said that the square root of x times the square root of x is equal to x. Well, does that also work for cube roots? Not exactly, but kind of. Anyway, on number 4, this would be the cube root of 9. And the cube root of 9 does not simplify. How about number 5? We have the cube root of 4 times the cube root of 4 times the cube root of 4. That's going to be the cube root of 4 times 4 times 4 is 64. And guess what? 64 is a perfect cube. So you can take the cube root of it, and that is 4. And so when I said not really but kind of, it's because these do work out. If you have the cube root of x and you have it 3 times, then that will equal x. And that little rule, both of these, are going to come into play here in just a minute. So make sure you really understand that that works that way. If it was the 5th root, if I had 5 of them, it would work out the same way. Okay, let's look at number 6 though. A little bit different. It is going to be the cube root. And what's 5 times 25? Well, it's 125. And so that also can be simplified because 125 is a perfect cube, and it comes out to be 5. I want to take a minute to explain this a little more because it ties in with number 5. Isn't the cube root of 25, couldn't I rewrite this? So I have the cube root of 5 times, isn't the cube root of 25 the same as the cube root of 5 times the cube root of 5? And so once again, we have 3 of them. They're all they're all being cubed. And so the answer is 5. Again, this little rule is going to come into play in just a minute with denominators. So it's kind of helpful, not even helpful, maybe imperative, that you understand how number 5 works, how number 6 works, and how they're kind of tied together. Because the last thing we need to talk about in this unit is rationalizing the denominator. And rationalizing the denominator, we've talked about it before in this class, and you talked about it a lot in in geometry. Also algebra 1, but you did it in geometry as well because you had the special right triangles. I think it's important that you understand the words. Rationalizing. What does that mean, rationalizing? Well, a rational number can be written as a fraction. An irrational number is a decimal that does not repeat and does not end, like pi, but also like other things. Like another common example is like radical 2, because that's a decimal that doesn't end and doesn't repeat. So when we say to rationalize the denominator, in this case today, what we're talking about is no radicals in the denominator. That's why it's called rationalizing the denominator. It's because we don't want radicals there. We only want integers, basically, in our denominators. So again, you did this in geometry, but we're going to take it a little bit farther. I'm going to go back and review. Remember, from geometry, what we would do is we would multiply both of these by the square root of 3x. And so what we get in our numerator is the square root of 3xy over, what does that come out to? It just comes out to be a 3x. Because we've been talking about that. Can that 3 and that 3 cancel? No. Can those x's? No. If they were both under a square root, yes, but the bottom does not have a square root, and so it cannot be canceled. Okay, number 2, what about cube roots? Let's go back to that little rule that we were talking about a minute ago. And the rule we were talking about a minute ago is if you have 3 of them, because it's a cube root, that would work. And so that's what we need to do. We need to do all 3 of them. Well, we need 2 more. Because we have 1, we need 2 more. So I'm going to multiply by the cube root of 2x and the cube root of 2x. But if I do it in the denominator, I have to also do it in the numerator. And so now, when I do this, I multiply straight across my numerator. I multiply straight across my denominator. And in the denominator, there are 3 of them, and they are cubed and cube roots. So we just get a 2x. That's the same rule I was referring to a minute ago. If you want to see how that's worked out, I could show you that this would be the cube root of 8x to the 3rd. And that little step is actually pretty helpful. I might stick with that here for just a minute. So we're trying to get to the cube root of 8x to the 3rd because 8 is a perfect cube and x to the 3rd is a perfect cube. And so that simplifies to 2x. In my numerator, as long as they're all under the same root, like cube root, square root, 4th root, whatever, you can multiply the numbers. So now they're all cube roots, so I can multiply 3 times 2 times 2. And 3 times 2 times 2 is 12. I have x squared, and I have a y. And now I'm done. The main thing was getting the radical out of the denominator, and I did that. Number 2 leads us into number 4 and 5. And I might kind of have them out of order a little bit because we need to talk about number 3, but number 2 really leads into 4 and 5. Let's go ahead and talk about number 3, and then we'll continue this line of reasoning that went with number 2. Now, number 3 is a little bit different because some people think we should just multiply by radical 14 in the numerator and the denominator. That's not actually going to work, so don't do that. Because what will happen in your denominator is you will get rid of the first one and it becomes 14. But in the second one, you get 2 radical 14, so you're back to having a radical in the denominator. That's not getting us anywhere. We're not going to do it that way. Do you remember conjugates? We talked about conjugates when we were doing imaginaries. So here what we need to do is we need to take advantage of the conjugates. This was radical 14 minus 2. I'm going to multiply by radical 14 plus 2. And if I do it in the denominator, I have to also do it in the numerator. So now I'm just going to distribute my numerator, and in my denominator, I'm going to do my double distribution. So in my numerator, I just have 5 radical 14 plus 10. I'm distributing. In my denominator, I'm going to have a 14 plus 2 radical 14 minus 2 radical 14 minus 4. Okay, let me show you that again. Radical 14 times radical 14 is 14. 2 radical 14 minus 2 radical 14. And then minus 4 on the end. And so 2 radical 14 minus 2 radical 14, they are gone. That's the beauty of a conjugate. They're gone. And so all we have is 14 minus 4. So let me rewrite what I have. I have 5 radical 14 in the numerator, and I have 10 in the denominator because 14 minus 4 is 10. These two dropped off. Now, if you wanted to, and probably we should, let's reduce it a little bit farther because there's a GCF of 5 in my numerator. And so I can factor out my GCF, cancel that 5, and make that a 2 in my denominator. And so that leaves me with square root 14 plus, I wrote that wrong. When I factored out my 5, that should be a plus 2 over here. I had plus 10. It's supposed to be plus 2. So change that if you wrote that down. That's supposed to be plus 2. So again, that 5 and 10 do cancel, leave me with square root of 14 plus 2 over 2. I would just leave it written like this. Some textbooks like to simplify that down to radical 14 over 2 plus 1. It doesn't matter. It means the same thing. Okay, let's get back to what we were talking about with number 2. Remember what I was talking about is that it's a third root, so you need 3 of them. Okay, same thing on number 4. But this time it's a fourth root, so I need 4 of them. Now, I will say that there is I call it a long lazy way or a short smart method. The long lazy way, let me show you real quickly, and I don't think I'm going to play it out all the way, but what you would do is you have a fourth root, you already have 1, so you need 3 more. And so I'm going to multiply by the fourth root of 3x squared 3 more times. And if I do it in the denominator, I have to do it in the numerator. And so now what I have in my denominator, and I said I was not going to play it out, but let's just go ahead and finish it out. In my denominator, I have 4 of them. They are all the same thing, and there are 4 of them, and it is a fourth root. So all I have down here is a 3x squared. In my numerator, I have a fourth root of 2 times 3 times 3 times 3. Well, 3 times 3 times 3 is 27 times 2 is 54. And x times x squared, x squared, x squared, so that's x to the 6th, x to the 7th. The problem with this method is that now we have to simplify further. And that maybe is not a problem to you. You're thinking, okay, I'd rather do that because it makes sense to me. That's fine. So now we need to simplify this. The 54 cannot be simplified any further. But the x's, I have 7 of them, and it's a fourth root. So I can get one group of 4 to come out. And if I do that, I'm left with 3 groups of 3 groups, or 3 x's inside. No groups, just x's. And so I come down to this, and now this x can cancel with this square, and now that is my final answer. You might try to write small to leave a little bit of space, or maybe space in the margin, where you can do the smart short method another way. But let me just go ahead and simplify this. So this simplifies down to the fourth root of 54, x to the third over 3x. Can that x cancel with one of those x's? No, because those are in the square root, or the fourth root, and this one's not under a root. Okay, that was the long, lazy method. But do you see what we did? We just multiplied. We got 4 of them, and we decided to do 4 of them because it was a fourth root. Let me take a minute. If I had multiplied these 4 together, done it like I had kind of skipped a step here when I did it, okay? Let's say I didn't skip that step. And let's say I have the fourth root, 3 times 3 times 3 times 3. Well, 3 times 3 times 3 times 3 is 81. And x squared, x squared, x squared, x squared, that is x to the 8th. And so the fourth root of 81, x to the 8th, the fourth root of 81 is 3. The fourth root of x to the 8th is x squared. So this is where that denominator came from. I would argue that 81 x to the 8th is actually bigger than we need, right? Because 81 is a fourth root. That's a good number to use. 81 is a good number to use in this case. X to the 8th is bigger than it needs to be. All we really needed was an x to the 4th, right? But when we did it, we weren't thinking of that. We were being lazy, and we just went ahead and multiplied all of them, which gave us x to the 8th. But all we really needed was x to the 4th. Let me show you another way to approach this problem. So I'm going to do the same problem, but I'm going to approach it differently. All right, so I came down here, and I just rewrote this problem. All I did was rewrite the problem, and I'm going to show you a different way to do it, and what I'm going to call this is the short, smart method. Okay, I had a 3x squared, and I want a perfect fourth power. Well, we talked about we have a 3 here, so what we really want to get is an 81 here, because 81, the fourth root of 81 is 3. So I'm trying to get to that. With my x's, all I really need to get to is x to the 4th. Well, what would get me there? So that's what I'm going to fill in this spot here is what would get me there. Well, I would need to multiply 3 times 27 to get 81, and I would need to multiply x squared times x squared to get x to the 4th. And if that's what I multiply in the denominator, I multiply that same thing in the numerator. This is going to add up or multiply out to be 81 x to the 4th. That's what I wanted. Because the reason I wanted that is because the fourth root of 81 is 3. The fourth root of x to the 4th is x. In my numerator, now since I took a minute to think about it and use my brain, nothing's going to have to be simplified later. So I have 2 times 27, which is 54. I have x times x squared, which is x to the 3rd. My denominator, I already figured that one out. My numerator does not need to be canceled any farther or any simplified in any way because I've already done my legwork at the beginning. Notice that answer is the same as that answer. Okay, so those are the two methods. And I'm going to go ahead and work on number 5 and show you how you can do it with that smart short method. I don't think the short lazy method or the long lazy method, I don't think it needs any more explanation. I'm going to teach you the smarter way. Okay, the first thing that you need to know, and hopefully you already know this, is that if you have the fraction, this is the same as the cube root of 3a over the cube root of 4b squared c. That cube root goes to both the numerator and the denominator. Okay, it is a third root. I have a 4. What perfect cube uses 4? What could I try to get to make and get to a perfect cube? I'm going to say let's try to get to 8. If you said 64, that's true. 4 to the 3rd is 64, but why get that big when you can just do 8? Okay, as far as the b's go, we want a b to the 3rd because it's a cube root, and we want a c to the 3rd because it's a cube root. Okay, well, what will we have to multiply by to get to that end result? We would have to multiply by 2 to get 4 times 2 is 8. b to get b to the second times b is b to the third, and c squared. C times c squared is c to the third. If that's what I multiply on the denominator, and it is what I multiply on the denominator, then that's what I also need to multiply in the numerator. So now in my numerator, I just need to multiply all that together because they are the same root, third root. I can do that. So this is 6ab c squared. My denominator, it can be simplified because that's why I set it up that way. So my numerator remains the same. My denominator, cube root of 8 is 2. B is just b, and same with c. So there are two ways, the long, lazy method or the short, smart method. You honestly can use either method. I do not care which one you do. Okay, that is all of the examples that we are going to work through. These problems, like numbers 4 and 5, I cannot find any in Delta Math, and so I think this assignment is going to be either a book assignment or a worksheet so that we can get some good examples of that.